Welcome to lecture 24 for Physics 4B. After some hiatus, while we covered enough magnetism needed, we return to circuits, having now introduced all three linear circuit elements to consider time-dependent circuits. We start with some circuit review in this lecture, and if it has been a while since you looked at our DC circuit lectures 16 and 17, I recommend looking at it again as we start our full treatment of RC, that is resistor and capacitor, and LR, that is inductor and resistor circuits. And in fact, the full treatment of RC and LR circuits take the remainder of this lecture. In our next lecture, we will look at the time-dependent circuits that exhibit oscillatory behavior, to be distinguished from AC circuits which are driven by an oscillating input signal. So these are what we are going to call linear circuit elements. The first is what you have seen before, resistor. That's described by this relationship, Ohm's law. Voltage is equal to resistance times the current. And the other two elements are what you have seen over the course of the semester so far. It wasn't introduced that way initially, but let me recast it and call them linear circuit elements. The second one is the capacitor, and that's what we are going to spend some amount of time today. So capacitor, the relationship that defined the capacitor was, well, I guess the version I remember is the definition of capacitance. It's the amount of charge stored on something, the capacitor, and the amount of voltage difference you had to put across the capacitor to put that amount of charge on the capacitor. Good? And the reason we haven't treated this as one unified thing is because we were waiting for the third element. We could not describe this third element until we covered the Faraday's law. That's why it had to wait an entire semester. We couldn't just come out with this right away at the beginning. So the third element is the inductor. It's represented with a symbolic version of a solenoid, a squiggly line. So what you have to imagine is that this is a solenoid. So it's characterized by some inductance L. And I guess I never talked about unit of inductance, right? I'll just give you the name. It's measured in something called henries. Just a name. It's SI unit, which means, if you plug in all those numbers into the formulas you have seen, it's going to give you the number in Henry. The relationship that defines an inductor is what we wrote down a while ago there. So the voltage change across the inductor is given by inductance times rate of change of current. Yep. Do these relationships look similar? Because right now you might look at it and say they don't look like each other at all. Like, how are they related? I'm hoping to show you by next week that you can treat this as three different things that actually belong in the same category. And that same category is what we call linear circuit elements. Circuit elements that obey a law that's kind of like Ohm's law. Right now it's hard to see it, but I'm hoping to get to that next week. And yeah, so let me start out with this. And today, the remaining 30 minutes or so today, we'll spend it on reminding you of the circuit stuff that you hopefully remember, or that if not, that's why I'm reminding you. And we'll give a simple treatment of a circuit containing two of the easier circuit elements, the resistor and capacitor. So let me start out with a reminder of a quick review of a circuit. And I think the quickest way to do it is through a circuit example. So I'm going to use this example circuit that you see on the screen there. So I guess it's kind of hard to guess from how it's built what the circuit looks like. So let me draw the circuit on the board. So call this circuit review. So what I have built on that breadboard is this circuit, which hopefully isn't too unfamiliar. It's a circuit consisting of 2 resistors, as you can see here. Circuit consisting of 2 resistors connected in this particular way. They're connected at a single point. And they are connected in such a way that I'm applying a voltage difference across both of them. So there's a voltage difference being applied here through use of this function generator. So let me say, all right, it's going to be the square wave thing that the function generator is generating. Okay? That's actually what you are seeing on the oscilloscope right now. That's the function generator signal. If I turn it down or up, then you see it changing. Good? All right. So it's a pretty simple circuit. 2 resistors in series, R1 and R2. And right now, all you're doing is measuring the voltage that you're applying. So it's not doing anything funny or interesting. So you can start to get to some more interesting things when you measure the voltage output across different parts of the circuit. So let's say I measure the voltage output this way at these 2 points, V out. So call this V in. So I have some amount of voltage that's being applied to the circuit. Call this V in. And I guess this is the question that we are trying to answer in any circuit question we have. What is this V out as a function of V in? So suppose you are asked this on an exam, like I could have asked you on exam 2. How would you go about answering this? Chris?
You would add up the resistors and use Ohm's law to find the current, and then use that current across R2 to find voltage.
Yeah, so add up the resistors. So the important thing here that I want to highlight before we get into the weeds of actually doing it is finding the current. The important thing here is finding the current, right? Once you know the current, then you can answer the rest of whatever it is I'm asking. So your entire goal here is, okay, trying to figure out what is the current in terms of the given quantities so that I can use this to find this, figure out this. Okay? So I'm going to go the long way. So in this circuit, it's simple enough that you can do exactly what Chris was suggesting. Add this in series. That's the equivalent resistance. Or use Ohm's law to find the current. And then multiply this current with the resistance. Then from Ohm's law, that gives you this voltage difference. Right? You all know how to do that. But because that method will not generalize easily to the next circuit that I'm going to have you look at, I'm going to apply the more general circuit solving approach with the Kirchhoff's rule that we learned earlier. So, as I'm going through this step, I want you to remember that this is the circuit we want to know how to analyze. This is the circuit. So RC circuit intro. This is the circuit that we want to know how to analyze. It's going to be essentially a copy of this circuit with some important changes. So I'm still going to have resistor R here. And in fact, I'm even going to have the same power supply here. That's going to provide me with some square wave. Now, the important part that'll change is that this part, instead of being a resistor, it'll turn into a capacitor. And my question will still be the same. What is this output voltage, V out, in terms of whatever parameters that we decided then will be sufficient to describe this. Okay? So this is what I want to put on your horizon so that it makes sense the sort of long, tortuous steps we are going to go through for this relatively simple question. Because, so you know, for this circuit, what Chris suggested will work. You add resistors in series. Can you add a resistor and capacitor in series? Like, I mean, they don't even compare to each other. So what we are going to need to do is we are going to have to set up a system of equations here. So that's why the method I'm going to use here is the set of steps that actually gave you system of equations. That's a Kirchhoff's rule, right? So that's the approach I'm going to use here, so that when we go to that circuit, we can use the exact same approach. So yeah, let me sketch out what we are doing here. So we are going to write Kirchhoff's rules. What do you get? Can you use the junction rule here? Do you see any junction that's non-trivial? I mean, it's a single loop, so you can define junctions, but you're just going to get trivial equations. So I'm going to end up, for simple circuits like this, I'm just going to end up using loop rule. Yep. Yeah, so let me do that. So let me define the loop. So let me call this my loop. So this is my loop. So applying the loop rule, this is what I get. Loop rule says the voltage change as you go around the loop should add up to 0. All right, so let's start from this point on the loop. I go across the power supply. Let's just say this is negative and positive end. So as I go across the power supply, I'm going to gain voltage of V in. And this might actually be a function of time this time. Before we are dealing with a constant voltage, this time we are saying, all right, it can be time varying. I go across the resistor R1. What's my voltage change? Yeah, minus the resistance times the current. That's that's Ohm's law. So minus, I prefer to write I first. So I R1. And then you go across another resistor. So that's the same expression. Minus the same current times R2. And come back here. So you complete the loop. That's equal to 0. So this is your one equation that you need to solve for. Simple enough to solve this for current I. So let me solve it for I. Then what I end up with is current I is equal to, so imagine moving this over, divide up by R1 plus R2. Then I get V in as a function of time, divide by R1 plus R2. Okay, now I know the current. Then I use this current to calculate this V out. As Chris said, multiply the current with the resistance. So that's going to be my V out. The current times the resistance R2, or plugging this in, it's R2 over R1 plus R2 V in as a function of time. But I'm hoping all these results sounds familiar. It's the voltage divider equation that you have seen in homework, and I thought you have seen it elsewhere too. But you have seen this multiple times. This is a familiar expression. Let me ask you this question. If I plot both V out and V in at the same time on the same graph, how do you think they will compare? Does V out rise at the same time V in is rising? Does it drop at the same time? Are they synchronized? When you look at this, is there anything here that says V out is not synchronized with V in? Right? So what's this ratio? R2 over R1 plus R2. What kind of quantity is that? It's a proportion. It's a sort of unitless coefficient because it's a ratio of resistances. So it's going to be on some number. Looking at this, it's actually going to be a number less than 1. because denominator is guaranteed to be bigger than numerator. So looking at this, you might say, okay, so V out is going to be smaller than V in. But other than that, there's nothing that says how V out changes as a function of time would be different from how V in changes as a function of time. Like, I'm not seeing anything there that suggests otherwise. So let's turn it on and see. So I turned off channel B here. Let me turn it back on. So channel B, pretty sure this is. Okay, so let me turn off the channel A button so that you can kind of see both channel A and B. So channel A, so channel B. In this particular circuit, both R1 and R2 are 1 kilo ohm resistors. So R1 is equal to R2, so you would expect this ratio is 1/2. And I set this to the same scale, like that looks like about 1/2, right? And if I decrease the input voltage, then they decrease together. And let's expand the time scale and see if they start and end at the same time. Oops, the other way. So you can really see it. But like this is the biggest scale I can get without things changing. Like this seem to rise and drop at the same time, right? Yeah. So this is a simple circuit. There's nothing complicated that we are expecting here. So now what I want to do, and spend the remaining 20 minutes or so to talk about, is how will the output signal look like if I replace this resistor with a capacitor. So this is one of the capacitors I have. It's a 10 microfarad capacitor. This is 1 kilo ohm resistor. And those are kind of a nice numbers to work with. That's why I picked them. But so when I have this circuit here, hook up the exact same voltage supply, voltage output, see what we get. I guess I could ask what you would expect to get, but I don't know how many of you have any kind of intuition for circuits. Like I could ask, but I'm kind of afraid of what kind of answer I would get. Yes, Chris?
I mean, won't it release the energy that's stored in the capacitor, so it shouldn't be on the same time schedule like this one was, right?
I see. So if we are starting to expect that the this shape of V out would be different from shape of, I didn't draw V in, that might be the case. But you will see that they are actually surprisingly synchronized. You know what, let me actually show you what it looks like, and then we'll try to figure out if we can make a sense of it using our equations. So let's see, my power supply is connected. Let me just connect my voltage probe. So right now, so far, channel B is flat because I haven't connected this. But when I connect it, now, hey, I get something that's not zero, but it's not nicely not zero. Let me expand the scale and see what it's supposed to be. Okay, just so you know, the scale is so far extended that, so the scale for channel B is 10 times the scale for channel A. What's going on here? Why is this so much smaller? It might be worthwhile to take the time to write down equation that governs this, and then we'll see if we can figure out what we can do to make the signal for V out bigger. Okay, so I'm going to follow this exact same approach we took before. So we are using Kirchhoff's rules again. Okay, I'm sort of trusting in Kirchhoff's rules as general problem-solving approach for any kind of circuit. So for exam 2, we are using this for battery and resistor circuits. Now what I'm doing is extending this to apply to circuits that contain capacitor, something that's not a resistor, but the rules are kind of generic rule. There's no reason it shouldn't apply here. So let me write it down. Kirchhoff's rules. So do I use a junction rule this time? Or no? Junction rule? There's still no junction here. It's just still one loop. So, all right, so I'm just going to use the loop rule. Loop rule says if you go around the loop, adding up change of voltage, that'll add up to 0. So I guess I better define my loop. So, I first should define my current. So I'll say my current goes this way. And my loop, I'll pick the same loop I picked last time. So loop that goes this way. This is my loop. So starting at this point, I go across the power supply, across the resistor, and then the capacitor. So, all right, I guess I'll just add them up. So as I go across the power supply, I gain voltage over V in. As I go across the resistor, I get a voltage drop of current times resistor. Yes, yeah, that part hasn't changed. Minus IR. This next part is new. What kind of voltage change do I get as I go across the capacitor? Let me.
I was looking at the formulas.
Yeah. So you are going to be using this relationship here. This is the defining relationship for capacitor. And one of the reasons, so you will, when you look at these expressions carefully, you will see that all of them contain an expression for voltage. So that's what really these expressions are for. For each of the circuit elements, they tell you how to get the voltage difference across each of the circuit element, so that you can express the circuit element in Kirchhoff's rules. So,
is it always voltage difference? Always change in voltage?
It's all change in voltage across the element. Yeah. So now I need to figure out the sign. So it's going to be either plus or minus. Solve that for VC. I get Q, amount of charge on the capacitor. That's new. Over capacitance C. So that brings me back to the loop. That should equal 0. I should spend some amount of time picking, is this going to be plus or minus? Just, sign error, whatever. So I guess this is the exercise I like to go through. Imagine I have these positive charges flowing this way. As they start to accumulate, if my capacitor wasn't charged, which end of the two plates end up being positive? Bottom one ends up being positively charged? Top. Yeah, visualize positive charges are moving.
Sorry.
They get blocked by this plate. They accumulate on the top plate. Positive charges accumulating on the top plate repels positive charges from below. So you get minus charges on the bottom. Okay? So if you go across from this side down to here, is your change in voltage positive or negative? Negative, right? From positive plate to negative plate. I do like to define my things so that my Q comes out positive if that's what I was, if I get what I was expecting to get. So let me make the sign here negative, so that if everything's as expected, my Q is positive. Okay? So this is my equation. It's how many unknowns do we have in this equation? Because I have to, at some point, I'd like to be able to solve this. 3 unknowns? How do you count to 3?
Sorry.
Okay, let's go through one by one. Input voltage, known or unknown? Known, it better be. Current through it, known or unknown? Unknown, it's one of the things we are trying to solve for. Resistance, known or unknown? Better be known, or we don't know what kind of circuit we have. Minus Q, is that known or unknown? Charge on the capacitor, you are not really given it. So yeah, you don't know that. Capacitance, known or unknown? You should know it, otherwise you don't have a complete characterization of the circuit. So I told you this is a 10 microfarad capacitor. And even if I didn't tell you what it was, you should treat this as an unknown. It's a parameter of the circuit. So I have one equation and 2 unknowns, which means it's not quite enough to actually solve this equation. It's in contrast to this equation which we could solve right away. So we need to do one more thing before we can actually start solving this. Sungmin, what do we need to do? We need to express a relationship for current. What's the relationship for current? So this is the one of the few times where I'm actually going to write this down. I'm actually going to write down current I is the actual time derivative of Q. And now I can actually say this because everything here is concretely defined. What I mean by Q, it's not some abstract charge flowing in the wire. What I mean by Q is the actual charges that are accumulating on the capacitor. Right? And this is the expression for current through capacitor. Because whenever you have some amount of current coming in, your amount of charge stored will change at the rate given by the current. Okay? Yeah, so once all this is in a circuit, then I can write down this relationship that some of you are wanting to write down that I wasn't writing down until now. So this is the thing that relates and now even though this is the current through the capacitor, because this is one loop, current through the capacitor is the current through the resistor. So I can use this even for this I here. So plugging that in, this is what I end up with. V in minus this, or let me pull out R to the front, R times dq dt minus 1 over c, q is equal to 0. What kind of equation do you end up with? Anybody have seen this in your math classes? It's a differential equation. You ought to have studied, I mean, even if you haven't taken differential equations, Math 3E, you should have seen this, something like this at some point in your calculus class, because that's where you introduce separation of variables, how to solve simple differential equations like this. But yeah, this is differential equation. And yeah, I guess that's it. So let me actually solve this for voltage difference across the capacitor. So voltage difference across capacitor, you can actually get it from here. So V out, what it should be is amount of charge on the capacitor divided by C. Right? So voltage across the capacitor is proportional to the amount of charge on the capacitor. Let me kind of solve this for that. Then what I end up with is, so V out or Q over C is equal to here, V in minus dq dt R times dq dt. So this is the expression, right? Yes. And when I look at this, I see that, hey, I see that my V out, it should be more or less the same as my V in. Why isn't it? Like when I look at this, it's clearly about 10 times smaller or more. So why is my output voltage not comparable to my input voltage? What do you see in the equation that causes my output voltage to be not at all similar to my input voltage? Not quite capacitance, because capacitance is buried here. So it's not the capacitance. Resistance is one. One more thing that we can blame that's easier to change. Where do you find the resistance? Yeah, in this second term, right? So it's the second term that's subtracting from V in that I'm going to blame. Why my V out is not at all similar to V in. So that gives me some idea. So, changing resistance, that's a little bit harder. I'll do it later. But I can try to change the rate of change of charge. So one control I have over rate is my period of the square wave. So if I make my frequency of square wave smaller, that'll change the rate of change smaller, right? So let me try that. So right now it's running at 1 kilohertz. Let me bring it down by a factor of 10. Oh, yeah, I have to change the time scale here to track the change. Oh, yeah, and I have to bring this back. Let me put them on the same scale because they are eventually going to start being comparable. All right, so it's now about half of so total change is about half of the total change of the square wave. Let me try even lower frequency. Oh. Okay, now that's making more sense. I mean, it's kind of hard to see because it's such a low frequency that kind of have to blink through. But imagine tracking this through several trigger cycles. All right. So this thing that I'm drawing in black is the input square wave, right? And let me trace the output signal across the capacitor in this shape. Yeah, they have about the same full size. And you can actually see when your output voltage is actually equal to the input voltage. That's whenever you somehow reach the state that this dq/dt is about equal to 0, meaning the current flowing through the circuit is about equal to 0. Then your output voltage is equal to input voltage. Okay? And it takes some time for the circuit to actually reach that state. When you run this at a higher frequency, what was going on was that you can describe this as the capacitor charging up. The capacitor is charging up from 0 to some value, and what you are seeing is that as the capacitor charges up, if you cut it off too soon, so if the square wave period is too short, then before capacitor has time to fully charge up, you would suddenly cut it short, so stop it here, or maybe that's a little bit too drastic. If you cut it off here, then the capacitor will stop here, and then it'll start discharging right away. And then, so when you cut it off like this, that's when you got the signal that looks like this for the capacitor. But when you wait long enough for this dq/dt to eventually go down to 0, or get something close to 0, then you see that the capacitor voltage reaches close to the input voltage. So what we done, do we have time for this? I guess we could actually put this off to your lab. So now that we have this equation, this is something we can do. So we have this equation, differential equation, in terms of a single dynamic unknown amount of charge on the capacitor as a function of time. So you can actually solve this differential equation. Do people here know how to solve this differential equation? Yes? No? Let me put that, especially if you don't know it, let me put it off to the lab. So I'm still finishing up your lab. I will put in an exercise for actually doing that, and I'll help you work through that when we get there. But for those of you who, you should know it, but because I guess your calculus teacher must have been terrible. I don't know. So I remember covering this in AP Calculus BC. So which means it should be covered in your calculus too. And this is a technique called separation of variables. It's a technique you can use to solve very simple first order differential equations. And this is an example of not too complicated first order differential equation, and using the technique called the separation of variables. Separation of variables, you can actually solve it. And I'll make sure to set enough time in the lab so that you can try it on your own and see if you can get a solution for Q of t that explains this shape. Because what kind of shape do you think this is? Like, this particular shape here. What kind of shape do you think that is? It's a curve, but it's actually not a parabola. I mean, for all the times people misuse this word, you guys are not saying it this one time where it actually applies. It's an exponential. It's exponentially decaying. It's a sort of inverse of exponential decay. So it's an actual exponential function shape. And when you solve this differential equation, you will see that as a solution to this q of t, you will see an exponential in there. Yeah. Okay, so what we are going to spend most of our time today doing is analyze the different types of this time-dependent circuit. So we were looking at the RC circuit last time, circuits with resistor and capacitor. And I think, I was hoping what you guys did in the lab would sort of wrap it up, but sorry, I gave you a more complicated problem in the lab. So we'll look at RC circuit again today and wrap it up. And I hope to have enough time to definitely go over LR circuit, a circuit with an inductor and a resistor, and an LC circuit where in an ideal case, there would be just the inductor and capacitor, no resistor. Okay, so let me draw the circuit diagram for RC circuit that we are looking at before. So when we have an RC circuit, could somebody remind me if, I was doing the square wave thing, right? With the RC circuit. Let me give you the simpler version. So in a simpler version, I can give you two types of RC circuit. So first type is this is the one that's, I guess, mathematically mathematically simpler. So I could build an RC circuit this way, where I have a capacitor and a resistor and nothing else, right? I mean, you can build this circuit, right? But you wouldn't get anything interesting out of this circuit because there's no battery there, nothing. So to get something interesting out of this, what you have to imagine is that you charged up this capacitor initially, so that you have to imagine that at time equals 0, you had some charge plus Q naught and minus Q naught on this capacitor. And that at some time you connected the circuit and then let current starting to flow, I guess, this way through the circuit. That's what you have to imagine. And let me actually combine this with the second type of circuit. So second type of circuit is a circuit that you needed to make this happen in the first place. So let me do that in slightly different color. So the second circuit would be if I have, let's say, I have a battery hooked up here. I want to hook it up so that this end is negative, this end is positive. And what I am going to have here is a switch network. So let me call this point A. Call this point B. And I have a switch between them. Okay? So when this switch is close to A, that's when this battery will charge up this capacitor. When this switch is hooked up here, I have a current flowing this way. And the current will charge up this side of the capacitor with a positive charge. And will eventually result in this shape. Good? Yes. And once it's charged up, then we could switch it around and say at time equals 0. At time equals 0, we are going to close this switch over to the B side. And then battery, we can ignore it. There's no current through this entire branch. We can just ignore that it's there. And then we have that simpler circuit that I initially started out drawing. Good? So let me do case 1 first, because this one is mathematically simpler. And then we'll look at case 2 as So the realistic version. So the thing that you're looking at in the lab, it's you kind of have to imagine where you flip this switch at a regular interval. That's what your square wave essentially is. Your square wave, when it's on, will be this portion, and then wait half a second, and then switch it to the other side. Wait half a second, there'll be the 1 hertz square wave. That's sort of switching between on and off. Okay, so let's wrap up part 1. I'm going to write down the equations quickly because we have done most of that on Monday. So let's say, so for 1, we are using Kirchhoff's rules. So the only rule I need to use is the junction rule. So junction rule that says, sorry, not junction rule, loop rule. Loop rule, so I'm considering this loop. Let's say, I want to draw my loop in the direction that the current is going. So when this switch is close to B, will my current flow clockwise or counterclockwise? Counterclockwise? Yeah, this is the positive end. So the voltage here is higher than the voltage here. So current will flow to the left across the register, and that's consistent with counterclockwise direction of current. Yep. So this will be both my direction of current and the loop that I'm picking. So going around this loop, let me start it from here. Starting from this position here, when I go through the loop, the sum of all the changes of voltage going through the loop is equal to, so going from one side, the lower voltage side of the capacitor to the higher voltage side of the capacitor will give me a gain in voltage. Anybody here remember how much amount of voltage? If not, this is the relationship I go back to. I'm dealing with the capacitor. This is the definition of capacitance. Anytime you're dealing with a capacitor, if you're not using this, you're probably doing something wrong. So, yes. Yeah, V is here. Yeah, Q over C. Yeah, do that quick algebra. So, all right. So the voltage here is the amount of charge on the capacitor. Q, I'm going to write this to remind myself that Q as a function of time over C, and plus because I chose my direction so that I'll get a voltage rise. And then keep going in the loop. As I go across this register, I'm going to lose a voltage of minus IR. I'm writing this as a reminder to myself that current is a function of time. That's equal to 0. So this is simpler than what we were dealing with the last time because it doesn't have an independent voltage source. So it's simpler. So let's just try solving this simple equation. So so this doesn't really calculus. Let's see. So this is what we did last time. So we look at how many unknowns we have. We see that we have 2 unknowns, charge and current. And if you just leave it there, we don't have enough information to solve it. So we need to bring in at least one more piece of information. What was that? Yeah, the expression for current through capacitor, that it's the derivative of the amount of charge on the capacitor. Because, and let me make sure everything is right. Yeah, this is where I have to be careful with the sign. If I have a positive current flowing, then the charge on the capacitor is decreasing, right? Yes? So as I have written it here, it's not quite right. Because as I have positive current flowing, my dq is negative. So I'm just going to do this, minus dq dt. Good? It's a matter of, which direction of current did I say was positive? Or, so this Q, once you have defined it, it can actually be positive or negative. It's a matter of which side you call positive side, and if it's charged actually the other way, then the amount of Q will be negative. So I always go through this exercise. I always think through, imagine the Q is changing from one particular way to some other direction that I think is natural. How does that direction of current match with the direction that I said was positive? And I insert whatever sign necessary here so that my definition of my sign conventions are consistent with each other. Comment, question? Yeah. Okay. Yeah. So anyways, if you didn't go through it, you'll see some sign error somewhere as you're working through the problem. Good. Okay. So I need to use this information to write down a single differential equation. So this becomes. So it becomes a function of or equation involving Q alone. I get Q as a function of time over C minus this. So minus plus R times dq dt is equal to 0. Okay. So this is differential equation, and unlike my physics 4A class, most of you have seen differential equation in your math classes, right? So actually, a lot of what we are doing this week and next week actually will be dealing with the differential equations. So just be ready for that. So when I see differential equation, I do the same thing that I do when I see a polynomial equation. Like when you see polynomial equation, the standard form to put in is where the highest order term is your leading term, right? And then you write down the rest. You do the same thing with the differential equation. You look at the order of derivatives. This says 0th order derivative, as in no derivative. This says first order derivative. So I'm going to solve everything here in terms of this first order derivative term. So let me write that down that way. dq dt, first order derivative, is equal to, I move this over to the other side, minus q over c, and then I have to multiply through by 1 over r. So minus 1 over rc q of t. So this is my differential equation in some kind of a standard form that's easier to tackle. So the step I'm going through now is what you are going through or were supposed to be going through in lab. Separation of variables and actually solving this differential equation. And I will tell you in this week and next week, you are going to see me approach differential equations in 2 different ways. So today, I'll be solving it mostly like a mathematician would, through proper steps, using separation of variable and all that. The moment I start seeing second-order differential equations, I'm going to stop doing that. I'm just going to guess a solution, and they will conveniently be right. Only because I know what the correct answer is before I guess it. But so, this one I can do the proper steps, so let me do that. I don't do that too often. So I use this approach called separation of variables. You are supposed to have seen this, I think, in your Math 3B class. You're supposed to have seen this already. If not, or if you don't remember, please review it. So the way I separate the variables is I look at the dynamical my variables here. Let me underline them in green and red. I have 2 variables here. I have, or let me box them. I have Q as a variable. Here's my Q. And I have T as a variable. Okay? And let me actually erase this for now. But because I think this statement that Q is a function of time, I think that's more confusing than clarifying. So when you look at it here, I have some quantities that are constant. These I don't worry about too much. I'll just let them lie wherever they are. What I'm concerned with here is these variables. And the solution technique here is I put all the terms involved, all the one type of variable on one side and the other type of variable on the other side. That's why we call it separation of variable. So I want to put all the Q terms on one side and all the T terms on the other side. And so, all right, I guess the easiest way to do here is move the Q over here and move dt over to the other side by imagining multiplying through by. So this is what you are imagining me doing. Take this and multiply through by dt over q. which is a bit of an abuse of notation because this dt is not just an algebraic symbol, but I'm not gonna be worried about that for now. I got other things to worry about. So let me write that out. When I do that, I get dq over q is equal to minus 1 over rc dt. And this is now an equation that you can solve by integration. Because left-hand side, you look at it for a while and you see, oh, this is something I can integrate. This says my integral is going to be in terms of q, and I have an expression in terms of only q. Like, I do remember q is a function of time, but here it's not written as an explicit function of time, so I don't have to worry about that. It depends on time. And this side, I have only constant, so if I integrate it, I'll just get t. So really, this step is the separation of variables, and the rest is just the simple integral. I guess it's not quite fundamental theorem of calculus, but you are doing a simple integral. Once again, I'm not going to be too concerned with the niceties of notation, other than one thing. So when I do integral, I will tell you this. In physics, I have found it very useful to get into habit of always doing definite integrals. Like, I never do an indefinite integral in physics, because in physics, there's really no reason ever to do an indefinite integral. Anything that you can do as an indefinite integral, you can do it as a definite integral. So when you do it as definite integral, this is what I say. So here's my integration variable. I want to make a statement that this variable takes on some value. It goes from some initial value to a final value. Right? And as this variable is changing that way, what was the initial value of time? The way I'm trying to set it up. 0, right? All right, so initial value 0. So as time changes from 0 to some final value, so this is the statement I'm making when I set the limits here. I say, all right, my charge q is going to go from some initial value that I will write down soon to a final value which I'm trying to find. So when you put in this limit, you are making that statement. You are saying, as this one variable changes from one to the other, this other variable changes from one to the other. Yeah. I found this to be useful because it gets, first it makes your integrals more concrete. You have to actually think about what's physically happening rather than just regurgitating memorized integral formulas. And also this ensures that you never forget your integration constant. Because when you do, how many times have you lost points in your calculus class because you forgot integration constant, right? There should be more hands. Yeah, but like when you do definite integrals, you never have to worry about it. It's automatically taken care of. So all right, so final value is something I'm trying to find. What is my initial value of charge? My initial value of charge. Yeah. Q naught. That's where you kind of have to read the problem and figure out, okay, what was my initial condition? Sometimes the problem doesn't give you one. Here I actually gave you one, that your initial charge was Q naught. So, all right, so Q is equal to Q naught. All right, that's it. So this is, as far as calculus problems go, this is actually a pretty simple calculus problem. It's the setting up part that's more complicated. So, all right, let's do this integral and get an answer. So let me start it here. So left-hand side, it's 1 over x. So I need to bring in logarithm. Antiderivative of 1 over x is logarithm of x. So left-hand side is natural log of q evaluated from limit of q naught to q final. Right-hand side is simpler. It's equal to minus dt, that's just t. So minus t over rc evaluated from limit of t equals 0 to t final. 0 to t final. Can I skip some of the logarithm algebra steps on the left-hand side? Because it's going to be logarithm of qf minus logarithm of q naught. That means if I combine the arguments, what do arguments look like when he? So I'm going to not write down a logarithm algebra step. tell me what the answer is if I do ln qf minus ln q naught. How do you simplify that? Yeah, right? The differences become ratios. Okay, so that's going to be the left-hand side, ln qf over q naught. That's equal to, right-hand side is easy, so I'll do that one. Minus tf over rc. Oops, well, I don't know why I turned the c into. All right, I want to solve for qf, my final charge. And actually, so I use that subscript f so that I don't confuse myself, this q with the other q. But at this point, what I would actually prefer to do is say that the final charge is a function of time. It's a function of a variable. And turn this tf as a variable t. Okay? Yeah, a mathematician would be more careful with this. Like they would probably put primes and do things like that. But it seems like too much hassle for me. All right, so I'm trying to solve for this q. So I guess what I should do is raise this. So this will become power of e. So that when I do that, so when I raise this whole thing to power of, or make it an argument to exponential, then exponential and logarithmal cancel each other out. And on the left-hand side, I will end up with q as a function of time over q naught. And on the right-hand side, it will be this raised to power of e. So e to the minus t over rc. Okay? And all right, let's go one more step. So actually solve for this, then you end up with q as a function of time is equal to q naught times e to the minus t over rc. So this is the simplest case. And I can kind of demonstrate it to you in a real circuit. So I took some time setting this up. Let's hope it works this time. So I have my camera. So let me actually build the real circuits that we are calculating. Oops. Real circuits that we are calculating numbers for there. And let's see if the signal, what we are deriving as answers actually happen, experimentally. So I worked out some of the values that would work out. So let's see. So I'm going to build an RC circuit. Here's my capacitor. This is a 10 microfarad capacitor, not that wait. Okay, 10 microfarad capacitor, and this is a 1 kilo ohm resistor. And this is RC circuit, right? And I'm going to connect from one end to the other. Wait, I guess. So what I'm supposed to do is charge up this capacitor, and then at time equals 0, just to connect this, short this so that you have a circuit, right? I can't really do it manually. So the way I'm going to do is I'm going to do it with a function generator. So function generator will be connected to these two ends. Ground here, and the positive voltage here. So when for some amount of time, there's going to be current flowing, charging up this capacitor. And at some time that I'm going to call time equals 0, the voltage of the function generator will go to 0. That makes the function generator behave like a simple wire. So at that time is when all of this starts. Okay? So let's try that. So I've connected the function generator. Let me turn on. Wait, is the time scale right? I'm at too high a frequency probably. Oh, okay, this is about right. Yeah, I think this is about right. So I have this. So I will, switch the camera to that. But for those who can see, actually, let me do it this way. So right now, what this oscilloscope is showing is the output of the function generator. And I have set things up so that there's just enough DC offset. Oops. So this is the position of the ground, 0 volts. And I put in some amount of DC offset on the function generator so that there's some period of time when the function generator is outputting 0 volts. And I have it triggered on a downward slope so that there are stuff happening to the left of what you are seeing. So imagine moving this over by half a cycle. That's what you are seeing there. All right, so let's turn on B, A, B, and connect this to the, so I want to measure the amount of charge on the capacitor. So I guess I can show this on the camera. So what I'm going to do is, the ground will connect itself, so I'm not going to really worry about it. I'm going to connect this end to this other side of the capacitor. That will measure the voltage across the capacitor, and that will be proportional to the amount of charge on the capacitor. So let me connect that there. And all right, I have to go slower. So it doesn't look like exponential right now because I need to go slower. All right, does that look like an exponential? Yeah. So that's what this result was predicting. That when you, so at this moment of time, right here is where, this is where t equals 0. And what the function, what the oscilloscope is graphing, the voltage on the capacitor, or voltage drop across the capacitor, this is proportional to Q of t, or sort of, which is proportional to e to the minus t over RC. And you guys looked at the time constant, this RC. This is what we call time constant. And you looked at it a little bit in the lab. For those of you who might not have gotten that far, here's one meaning of time constant tau that we can assign to. So when time is equal to tau, then this factor becomes e to the minus t over RC becomes e to the minus 1. Or in terms of charge, your Q of t would become Q naught divided by E. This is approximately equal to Q naught divided by 3. E is like 2.7 something. So if you're trying to figure out time constant on this graph, then what you do is, all right, you look at how much the voltage falls to 1/3, or falls by 2/3. So it's starting at 1, 2, 3, 3 and a little bit more division. Let me actually make it 3 divisions. I have control over my function generator. All right. It's almost the 3 divisions now, right? All right, so when it's exactly 3 divisions, then where it crosses here, this is supposed to be, so this amount of time here, that's supposed to be the time constant. Let's see if it is. I was telling you what the values of the resistor and the capacitor were. The capacitor, let me double check it, is 10 microfarad. So here I have R equals 1 kilo ohm, and the capacitance of 10 microfarad, meaning my time constant tau is equal to 10 to the 3 ohm times 10 microfarad will be 10 times 10 to the minus 6 farad, or 10 to minus 5 farad. I'm just going to trust my SI unit system and believe that ohm times farad is going to be seconds. You can do it on your own if you don't trust it. So the time constant here should be 10 to the minus 2 seconds. So this better be about 10 milliseconds. So that looks like about 1 division. I hope I'm on 10 milliseconds per division scale. I am on 10 milliseconds per division scale. In case you don't believe, yeah. Good. So yeah, so everything agrees here. All right, good enough. All right, so this is the simplest time-dependent circuit you can solve for. But it's kind of simple. It's a very special case scenario. What I find is simpler to do in lab is actually the other scenario, the scenario number 2. So let's go through scenario number 2. I will do this as the modification of this. I'll try to set up things so that it's modified properly. So let me do it this way. I want to set it up so that the current actually, when I hook up this battery, current actually now goes clockwise. So this clockwise current is going to be charging up the capacitor. So we don't have this anymore. Let me erase it so that it's not confusing anyone. So when this switch closes over to A side, now what you're going to have is you're going to have current flowing clockwise. So this will be the direction of current and the loop that we are going to use. Okay? And how do I not put it? Let me do this. Yeah. So let me say that the amount of charge on the capacitor is going to be plus Q of t and minus Q of t. And I'll say, to make things simpler, at time equals 0, that Q of t is 0, that it starts out uncharged. And at time equals 0, I'm charging it. So, all right. Does the direction I labeled the plus and the negative charge make sense? If it starts out from 0 charge, as current comes in, you are going to have positive charges accumulating here. So the way I labeled it makes sense. All right, so I think I have all the diagrams. Let me write down the sum of all the voltages. So actually, I guess let me start my loop here. That makes it easier to use what I already have there. And so this time, my loop is actually going from positive to negative side of the capacitor. So instead of plus Q of t, this is going to be minus Q of t. This is still minus IR. Why do I not have to change the sign of this term? Yeah, so with the resistor, what matters is the direction of current. And I'm still going with the current. So it's still minus IR. Let me write down the term that I gain as I go through the battery. I should have given the voltage, voltage of the battery is V naught, a constant value. So I'll get plus V naught from here. So plus V naught is equal to 0. All right. So we still have these two unknowns. This is what we wrote down before. Let's just double check that it is still correct. That as positive current flows, my dq dt, is that positive or negative? Is Q increasing or decreasing as positive current flows? It's not decreasing. It's increasing from 0 to this non-zero value, right? And I oriented it so that it'll charge. So this time it means this is plus dq dt. So that's why I like to go through this rule, go through this check every single time. Otherwise, there's a chance that you might make a sign error. I haven't found any other way to avoid it either. Yeah.
Go through the steps again. You look at the direction the current goes. And
So I imagine what happens as a positive current flows. If as a positive current flows, if Q of t is decreasing, then I have to have minus sign like I did last time. If you find that it should be increasing, then I should have plus sign. Okay. Good? Yeah. I mean, I'm sure there's some other thing you can look at to see if your sign conventions are consistent, but this is the easiest way I found. Just make sure your signs come out right. Yeah. All right. So let's imagine plugging this in. Then I get more or less the same equation as last time. It's going to be, so Q of t over C, minus Q of t over C, still plus, wait, not plus, actually this becomes minus, right? Because I'm putting this in here, so it's minus R times dq dt, minus R dq dt, And I guess I'm just going to erase the rest of the board because at some point I'm not going to be able to reuse what's already on the board, and I need more space. So I have a third term this time. It's going to be plus V naught is equal to 0. Good? Everyone okay with this differential equation we get from applying Kirchhoff's loop rule? Okay. So I'm going to do the same thing as last time. I'm going to solve this equation for dq dt. And I can already see that it's going to be significantly different. So let me just erase all of this and just write out what it is now. So it's probably going to be, or it's going to be, so move dq dt over to the other side and write that down first. dq dt is equal to the other terms remaining on the original side, V naught minus 1 over C. And I'm actually going to multiply through by 1 over R also. So it's going to be V naught over R minus 1 over RC Q. Everything good? Okay. All right, so I'm going to separate variables again. So on the right-hand side here, I have a term that depends on Q, no dependence on time. So I want to do the same thing as last time. Collect all the Q terms on the left-hand side and all the dt time terms on the right-hand side. So how do you get this term to the left-hand side? I guess it's essentially a choice of this is the choice before you. Do you add on both sides by plus Q over RC, or do you do something else? Like if you did this, will this work? If you did on both sides plus Q over RC plus Q over RC, will that work? The answer is no. It's because doing it this way, you have no way to separate dt from dq. Like after this, imagine multiplying both sides by dt. Then you are going to be left with the crummy dt term here, where you want to get rid of it. And but now this is tied to the q, so you can't move it back either. So here, really the only way you can separate q and t is actually the exact same thing that you did the last time. You have to divide both sides. And this time, I'm going to divide both sides by, let me do it this way. This is the version I like. I'm going to divide both sides by 1 over C V naught minus Q. So times 1 over C V naught minus Q. There's a reason I'm doing it that way. So to simplify it, I should simplify this, write it as multiply top and bottom by C. So this is C V naught minus Q neatly cancels this. And on the right-hand side, I'm just left with 1 over RC. On the left-hand side, I'm left with whatever. And I'm also going to move dt over to the other side. So let me write down the simplified version where all of that has been done. So this is the simplified version where all of that has been done. So this is the step that we would call separation of variables. Then you have on the left-hand side, dq over C V naught minus Q. Okay. On the right-hand side, we have 1 for the, or we have dt for the numerator. So it's dt over, I did something wrong. I'll fix it. So I have dt over RC, but I actually don't like that. I guess I could leave it that way. No, I'm going to put it in a format that's going to make it, put it in a format that it's eventually going to be anyway. So, these little tiny fixes I'm making, if you don't do it, it doesn't matter. Eventually, your final answer is going to have the same form either way. I just want my current answer here to reflect what it's going to be in the end. So this is what I get directly out of this. And what I feel like I'm missing is I feel like this side should have a minus sign. So the way I'm going to get that to have minus sign is I'm going to multiply through by -1. When I do that, I get this minus sign that I want you to see. And the denominator here becomes plus q minus CV naught. That's something neurotic I'm doing. Got any questions? So far here, nothing looks all that unusual, right? Yes? No? Good? Yeah? I just want you to see it that way. So I don't have a good reason other than that's what I find natural. If you don't do this step, that's actually fine. If you go through all the steps that I'm doing from here on, you will eventually find that the minus sign shows up again so that your final answer for Q of t ends up being the same no matter what you do. I just like this way better. Okay, I guess here's one way I can justify it. I kind of want to see plus sign here in front of Q. That'll make my next step actually easy. So I have the variables separated, right? Everything on the left-hand side depends only on Q. Everything on the right-hand side depends only on t. Nothing, or it's constant. It doesn't. But the important thing is that it does not depend on Q. So what that means is we can do the exact same thing we did last time. We can integrate left-hand side and the right-hand side. Let me do it as a definite integral again. So the right-hand side integral goes from t is equal to 0 to some value t final. Left-hand side integral goes from q is equal to, what was my initial value of q?
0.
Yeah, this time it's 0. So it goes from q is equal to 0 to some final value q final. Who knows what that is? We are trying to find it. Good. So we do the integral and we go through all that. And let me do the next step in a way that most of you didn't do it that way during lab. So this is how I'm going to do the next step. So most of you in the lab, you did a u substitution to do this integral, right? Is that what most people here did? Okay, I'm not going to do u substitution. I'm just going to guess and check. I'm going to guess that my antiderivative of this is natural log of q minus cv naught. Does it? It feels like the right answer. So the way you check it is you plug it, you take the derivative of it. Do you get this back? Right? You get 1 over this times the derivative of the inside, which is 1. That's kind of why I wanted this plus sign here. Makes it easier to guess. So yeah, this is actually correct antiderivative, which means I can do this. I can say it's a natural log of q minus cv naught evaluated from q is equal to 0 to q final. Turns out this is actually the simplest thing you can do mathematically. Now, it might not make as much sense, especially if you haven't done as many definite integrals as I have. In case you do u substitution, let me show you what you have to do. So if you do the u substitution, where you say u is equal to minus cv naught plus q, and du is equal to dq, then there's one more additional thing you have to do when you are doing definite integrals. You have to take care of the limits. You can't just leave the limits alone. Because there's a reason I always write the limits this way. This is saying q is equal to 0. It doesn't say what u is equal to. So if you are changing your variable of integration, you have to re-express your limits in terms of your new variable of integration. So you have to plug all those in to say, this should end up saying, so du over u integrated from when q is equal to 0 minus cv naught to when q is equal to q final minus cv naught plus q final. So you have to remember to do this as well as the rest of the other things. That's why I find it easier to simply guess my antiderivative and don't do any other substitutions. Okay, so let's continue. So that was the left-hand side. The right-hand side will be the same as before. It's I'll just plug in the limits also actually. Minus TF over RC. Okay. Let me plug in the limit. Then I have natural log of the upper limit QF minus CV naught divided by, I'm skipping the logarithm algebra step, divided by when Q is equal to 0. So minus CV naught. Did I do something wrong? It'll work out. That's equal to minus TF over RC. And I'll do the exact same thing I did the last time. I'm going to reinterpret what final means, because there's no actual final point. This F was just a reminder to me that it's a distinct quantity. So I want to just express that as Q as a function of time. And this T final is just some time T. Good. All right, so I have to go through a couple more algebra steps to actually finish solving it. So raise both sides by the power of exponential so that the logarithm cancels. So I have Q, so what I have is Q of T minus CV naught over minus CV naught is equal to exponential of minus T over RC. So we are going to have another exponential decay somewhere, somehow. All right, I have to finish the algebra. Multiply both sides by minus CV naught. So that ends up with Q of T minus CV naught is equal to minus CV naught e to the minus T over RC. All right, so to finish solving it, move this over to the other side, and I can actually factor out CV naught. Then when I do all of that, this is what you finally end up with. Q of T is equal to CV naught factored out. So I have 1 plus 1 minus this, e to the minus T over RC. I think some of you actually got this in your lab, but in case you didn't, this is the term that you are supposed to end up with. It's not quite as simple as the other one. It's not simple exponential decay. I mean, there is actually an exponential decay here. It just happens to be the thing that's subtracting from 1. And if you want to see this on the oscilloscope, it's actually very simple what I have to do. The very simple thing I can do is instead of triggering on the downward slope, I can trigger on the upward slope. Then my definition of time equals 0 will change. Yeah. So what you have to imagine here is on the left-hand side, there's this portion of the square wave. So at the end of this square wave, I more or less discharge the capacitor. So you're starting out with a 0 charge on the capacitor. And this curve here, it's not exponential rise. What it is flipped over exponential decay. As in this flipped over exponential decay, subtracting from this asymptote value of 1. Okay. So yeah, so that's what you get. Yeah. Good, questions, comments? All right, so that's the RC circuit. And so how we approach this circuit will be model for the, well, it'll be at least the model for LR circuit. And we'll do LC circuit in an entirely different way. Welcome back. So, so this is LR circuit. I started drawing some of it to save a little bit of time. Let's see, what else? So, oh, I guess we can look at that here. So this is a typical model of an inductor. It's this toroid that I've been showing around and passing around. You've seen this toroid in front of you before. So this is a typical model of an inductor. You can calculate come up with the formula for inductance of this. This exact same way we did it for the solenoid. So for here, what's important is that this has an inductance that if you can calculate it, you can at least measure it. So I got this inductance meter a while ago. So we can actually measure the inductance right now so that this inductor that we are using, we can just measure its inductance and just use that value. We don't have to, calculate it or whatever. So it'll do its measuring thing. And when it measures, I want to write it down somewhere so that I don't forget. All right, so I don't know if everyone can, yeah, you guys definitely cannot see this. You will have to take my word for it. Here, it says mH. So what it's saying is that this is the value of the inductance. It's saying that the inductance here is 7.4 millihenry, or 7.4 times 10 to the minus 3 Henry. And if you look at it really carefully here, or you can do it after class, there's a little omega symbol here. I set it on a mode where it measures the resistance of the inductor. Now, ideal inductor doesn't have resistance, but it's made up of real wire. So it actually has resistance of 1.47 ohm, which seems reasonable, right? That's the kind of resistance of wire that you have seen of a reasonable amount of length, like a meter, right? Yes. Okay. Yeah. So all right. So that's our inductor. So we are going to use this inductor. So this is the thing about the inductance. It's a property of this object. It's determined by the property of this core that I'm using and the geometry of the wire. So once it's determined, then as far as the circuit goes, once you know the value of the inductance, then you just use it. You don't have to worry about anything beyond that. You just have to know that it's a constant. Good. Okay, so we are using this inductance to analyze this inductor resistor circuit. So let's go through the same thing that we did for capacitor circuit. Imagine that, so actually we are going to go in the proper order this time. We are not going to say the inductor is charged up for some mysterious reason. We'll say it starts out uncharged. It's just a coil of wire connected to resistor. So if I want to complete start building the LR circuit, where I have this one end of inductor, I'd hook up a resistor there. So that would be my LR circuit. This is 100 ohm, by the way. I got different resistance. And nothing interesting is happening until you connect it to a battery. Good. So let's say at time equals 0. At time equals 0, we connect it. How much current do you think would flow at the exact moment when you connect the battery? Or like exact moment right after when you connect the battery? What would you say is the amount of current that flows at time equals 0? Any guesses? Intuitive guesses? Yes?
Could you just add the resistance of the inductor and the...
Yeah, so once again, I would not do that. Any kind of formulas and things that you memorized by rote for resistor circuit, forget it. It's not going to apply. Because that's the point of looking at this, right? The way resistor behaves in a circuit, it's of an entirely different kind from inductor. Whatever you thought worked with the resistor does not work with inductor. Inductor does not have resistance. So this says that R, but for here, just imagine that it's an ideal inductor. And the question is, how much current will flow that at the exact moment? So whatever you are considering, if it doesn't account for the fact that this is an inductor, you're not doing it right. So otherwise I might have just replaced the wire. So you have to think through the property of inductor. So as you think through the property of inductor, this is where you can see if you actually understand what an inductor is beyond just knowing that, oh, that's the definition of inductance. So I think the equation I consider when I try to understand the qualitative behavior of an inductor is this, that the voltage change across the inductor is equal to inductance L times di dt. I mean, I'm just taking this same expression here, solving it for v. So you have to visualize, go through the consequences of, I guess it's probably good to guess and check. So here, if you are, I don't know, trying to guess what value of I would be. Let's say we are trying to make like, so we are not trying to guess an exact value of I, because that would be too difficult. Let's try to make it multiple choice. Let's imagine all the different values of that I could take. One particular value in one category and other values in a different category. Any value you think would be special? Yeah, 0 is a special value for many reasons. Here I can at least give you one other reason than the usual reason. I can say, well, here the reason 0 is special is current at time less than 0. Well, that was actually 0 because that was before you connected it. The current through the inductor was 0 before anything was connected. All right, so 0 is one type of value. So if we are trying to guess multiple choice A and B, we might guess the current is equal to 0, or we might guess current is not equal to 0. How many think it's A? How many think it's B? Yeah, so if you think it's B, what other value do you think a current can be? So let's just, if you don't have a good guess for other value the current can be, let's just start out with saying, all right, let's suppose it's not equal to 0. So I'll tell you to start out with the correct answer. So correct answer is 0. So what I'm trying to do now is what someone might call proof by contradiction, although I won't go through the whole rigorous thing. But I want to kind of show that this is impossible. So in physics and math, to show something is impossible, you assume that the impossible thing happens. And when you follow the logical consequences of that, at some point you will hit something that's absurdly, patently false. That's when you know the thing that you assumed was incorrect, therefore it's impossible. Good? So I'm going to assume that the current that's flowing right now, it's not 0, that this is some value, I naught. All right, so I want to go through some consequences of what this means. I feel like it'll be helpful to have a plot. So if I plot my current as a function of time, this is what it means. Let me say this point is time equals 0. So my current was 0 up until this point. And at time equals 0, it takes on some other value that I'm going to call I naught. And after that, who knows? It might be increasing, decreasing, staying constant. I don't really care. But it's up to this point that I have the mental picture worked out. And I want to find something here that's inconsistent with the other features of the circuit. And my main tool is, well, what's listed here, and mostly especially this. Like, what do you see that's not physically possible? Current can depend on time, and that's not. So okay. I find so what I'm imagining my role to be right now is to be someone who provides all the counterexamples. So you guys are some of you are thinking, can current depend on time? Sure, it can. Here's one easy way I can make a current depend on time. I can take this circuit. And I'm going to build a separate circuit here. I'm just going to build a resistor circuit with a 1 kilo ohm resistor. And what I'm going to do now is connect this voltage source across this 1 kilo ohm resistor. Good? Let me turn off B because I'm not doing anything with the B right now. So what you're seeing here right now is the voltage for A, right? And you see, well, it depends on time. The voltage was some value, and then it's 0, and then it's some other value. And here, because that voltage is across the register, according to this relationship here, I is equal to V over R, your current is exactly the same function of time that V is. So current can be function of time. Current can change. That part I find no problem with. But what you may have to look at with more detail is how current depends on time. Yeah, so that is an important thing, that this voltage here is proportional to the rate of change of current, not the current itself. If it was proportional to current itself, I would have no trouble with that kind of current change. So when you have this kind of change in current, how does that cause difficulty when you have an inductor in the circuit? So actually, when you see change that looks like this, how large is your didt? Like very large, right? It's this slope. It can be infinite depending on how you idealize this. So that means if you have infinite didt, you have infinite change in voltage. But in this circuit, I have only finite amount of voltage here, V naught. So that's the contradiction I was looking for. If I want to say my current suddenly changes to a new value, this requires an infinite rate of change when it happens. So I cannot have an infinite rate of change without an infinite voltage. Here's another way to intuitively, sort of conceptually explain this. Inductor resists, not current, the resistor resists current. Inductor resists change in current. So whenever you have inductor in a circuit, current can only change at a finite rate. What that means is that when you graph your current plot, so it can change as a function of time, but it'll have to change as some non-infinite rate or finite rate, so that the current as time, this curve will always be continuous. Yep. So so what we can say is that, okay, at time equals 0, my current is still 0. And the rest of what we are going to work out is going to describe how this current changes from 0 to some other non-zero value. Okay, so let's actually go through the rest of the math. So this is really the point that I want you to get across, that inductor resists the change in current. So that whenever you have inductor, all right, so I have this circuit. I want to write my analysis, so I will do the same thing we were doing before, define a loop to write down my Kirchhoff's loop rule. So I want to reuse as much of that as possible. So I would have to define my loop this way. Starting here, I think I want to go clockwise again and go this way. All right, that seems reasonable. Okay, any questions? No? All right, so this is the leftover from the RC circuit. So I'm going to change, so this part is the same. I'm going to change some of these terms so that it now matches with my LR circuit, and I'll do that in black. So the very first term, this was written in for the capacitor, which I don't have anymore. So I should change it with my inductor term. So I'm looking for voltage difference as I go across the inductor. Well, lucky me that I already have that written there. So it's going to be inductance times di dt. I have to go over the sign. Is it plus or minus? So this is where you kind of have to think it through. So I hook up the battery. So there's going to be positive current starting to flow. Well, starting from 0. And what I'm interested in is actually sign of di dt. So will di dt be positive or negative as I don't know, hook up the battery and charge up the inductor? Positive, right? Di dt increases from 0 to some non-zero value. We'll just define this direction as being positive. All right, so they'll be positive. Now the voltage change across inductor. Do we want a voltage rise or voltage drop? Like what makes it intuitive sense to you? That the voltage should rise or that the voltage should drop? Drop, right? It takes effort to put things through the inductor. So which means the overall term that I want to associate with this should be a negative term. So since di dt is positive, this should be minus L di dt. Good? No questions? Okay, so I don't have Q anymore. So the problem is that thing in the box is not going to be needed. So let me erase that. All right, can I leave this one alone, the one with the register? Yeah, minus IR, seems right to me. Can I leave the third term alone? As I go across the battery, plus V naught? Yeah, actually I can leave that one alone too. Looks like I'm done. How many unknowns do I have in this equation? Just one, I. So in some sense, actually, inductor circuit is simpler than the capacitor circuit. The reason with the capacitor first is because I think a capacitor is conceptually easier to understand. Inductor is conceptually harder. Even the whole, this thing that inductor resists the change in current, it's a more advanced concept than, so anyways. But yeah, so this is the equation. And so I see the only unknown is current. So really my goal here is to solve for what current is as a function of time. And once I know that, then I can find out anything else I want. I can find out the voltage across inductor, whatever. Yeah. So let's go through the steps to try to do that. I'm going to do the same thing I did the last time. Solve this for the highest order derivative term. Right? So I'm going to solve it for di dt. That's equal to, so I move this over, divide that by L. So I'm left with V naught minus IR, and I divide it through by L. All right. So separation of variables again? Yes? Let me do a couple, a simple algebraic manipulation before I do the separation of variable. I want to collect terms in a way that will make sense later on. So I want to collect terms this way. V naught over L minus R over L times I. And for a reason of my own, I'm going to rewrite this way. Let's see. I'm going to rewrite this as, how does it go? I want to factor out 1 over L over R. Don't ask me to explain why, only that what I'm doing is mathematically valid. I want to factor out this 1 over LR, which may sound strange because first term doesn't have any R. But this is what I mean by factoring out 1 over LR. This term is going to turn into V naught over R. You see how this is the factored version of this, right? Multiply this, you get V naught over L. Minus just I. Okay? Any questions? So there's a reason I factored it this way. The thing I have factored out here, it's a constant. It only has L and R in it, right? And so, you know, when I do separation of variables, I only need to move this term over to the other side, because this is the only factor that has a variable I in it. Good. And there were a couple other ways you could have done this, but the particular way I did it, it has one more additional advantage. And that advantage is that this particular quantity here, L over R, if you work out the unit on your own, you will find that this has a unit of time. So if you're thinking back to how you figured out the time constant for the RC circuit, this is the time constant for the LR circuit. So we'll go through the math and see where that comes in. So, all right, so having done all of that, let me actually go on ahead and separate the variables. So separation of variables gets me this. So I'm going to collect this term on the di side. So I have di over v naught over r minus I. That's equal to, I'm going to move dt term over to the other side. Dt divided by L over R. I have the urge to multiply this through by -1 again, but this time let me actually do it the other way. So let me show you what you would have gotten if you didn't multiply through by -1, like I did last time. So here, does everything look okay if we just start integrating now? Right? Yeah. Everything here in terms of I, everything here in terms of t, and it's nothing other than t. So yeah, I can just actually start integrating. So let me do that. So here the integral. So I'm always going to do definite integral. So that means I have, say, it's t equal to 0 to some final time t final. So here current, what's my initial current? Yeah, 0. So I goes from 0 to some final value, I final, that I'm going to find later. All right, and I'm going to actually do the same thing I did the last time. I'm not going to do any u substitution. Oh, actually, let me do it the other way. Let me do the u substitution. So this time the u substitution will be, all right, I have this thing, so I do this substitution. U is equal to v naught over r minus I. So du is equal to minus di. Good? Plug it in. This is what you end up with. Di becomes minus du over, this becomes u. And when you integrate it, now you have to remember that you are putting the limits in terms of u. So for the lower limit, you plug in I equals 0. So u, whatever that is, goes from v over r to u at the upper limit, v over r minus I final. V over r minus I final. All right, so that's the left-hand side. Right-hand side doesn't actually, well, let me just do the right-hand side. It doesn't look all that complicated. So do the integral. It's t over L over r. Plug in t final. So you end up with the t final over L over r on the right-hand side. Yeah. And if you want, this is the step where you can actually move the minus sign over to the other side. So whichever way you go, you will eventually end up with your minus sign on the other side. So let me actually do that now. Multiply through by -1, now that I have some reason to do that. So this becomes plus, this becomes minus. Good. Okay, let's wrap this up. So the antiderivatives of 1 over u is logarithm. So it becomes, so the whole equation here becomes the natural log of u. So I'm just going to plug in the limits at this step also. So upper limit, v over r minus I final. V over r minus I final. So ln natural log of this minus natural log of this simplifies to natural log of upper limit divided by natural log of the, or divided by the lower limit. V over r. Close. Good? Questions? All right, so all of this is equal to this. So let me write out the cleaned up version over there and solve it for I final. So this is the cleaned up version. Natural log of v over r minus I final over v over r is equal to minus t final over L over r. So a lot of steps will begin to look familiar because you have the natural log again. So you are raising this to power of e again so that you get rid of natural log. So the left-hand side becomes V over R minus I final over V over R. That's equal to here, e to the minus t final over L over R. So this is where it actually begins to look like the time constant that you saw last time. All right, so I have to solve for I final. So what that means is I multiply through by V over R. So V over R here, move I final on to that side, move this over to this side. Okay? So when I do all of that, this is what you end up with. I final is equal to V over R that was left over on the original side minus this term that you moved over. V over R times e to the minus t final over L over R. Everyone good with this so far? Yes? Okay, so let me factor out V over R. I mean, that was the obvious thing to do. Factor out V over R, and I end up with 1 minus e to the minus t final over L over R. And let me do the thing that I've been doing so far. So I don't really want to be talking about the final time. This t final really is a stand-in for the variable time. And this I final is really I as a function of time. Okay? So this is the expression. And let's see if we can get it. So I have this circuit here that I've been building. So I have an inductor in series with a resistor, and I'm going to do the same thing I did with the capacitor. When I hook this up, so I want to be measuring current, so that means I want to be measuring voltage across the inductor. So let me hook this up this way, across the resistor through the inductor here. Some things have changed. I want you to ignore that for now. A lot of things have difficulty driving inductive load properly. So I want you to ignore that for now. And I'm going to try to measure the voltage across the resistor here. I don't really have to attach the ground. Turn on channel B. Something doesn't look quite right. It might be a matter of the frequency that it's at. Okay, yeah, need to be faster. Maybe a little bit faster. Okay, only a little bit faster, not a lot faster. All right, that's probably good enough. So just so that you can tell which is A and which is B, this is A, that's our driving. So once again, it's supposed to be square, but it's not square because the power supply is having trouble following the path that it's supposed to be following. But so I want you to focus on B. So I need A. So so focus on this B. And the left edge of the screen is the time equals 0. That's where it triggers on the rising edge. So that's where my applied voltage went from 0 to a positive value. And what you see here, does this curve here, does it look like it will be described by this? Yeah, it's the inverse of the exponential decay, right? Yeah. What's this asymptotic value of current? What's this asymptotic value of final value of current? When you look at this expression. V over R, right? So voltage of the battery divided by the resistance of the resistor. Does that make sense? Like looking at this circuit, that if somebody told you that the maximum amount of the current that would flow is this voltage divided by this resistor, as though this inductor isn't there, does that make sense? Yes?
Is this because of the inductor being ideal with no resistance in it? Or?
Yeah, let's say, even though it does have resistance, in this case, it's actually close to ideal because the resistance of the inductor was 1.4 ohm. The resistor here is 100 ohm. So you could actually ignore this. So But I want you to focus on the property of the inductor itself, not the fact that it's ideal. Like, what about the inductor allows you to ignore it towards the end of this charging cycle? Because that definitely wasn't the case with the capacitor. With the capacitor, you know, when it got fully charged up, it dropped the entire voltage of the battery so that there was no more current flowing. But with the inductor, we are saying almost what sounds like the exact opposite thing. We are saying that when it's fully charged, we can kind of ignore the influence of the inductor altogether. Yes?
Is it because there's less change of current, or change of current approaches zero?
Yeah, so you still focus on this, dIdt. So you look at the rate of change of current. And as Chris said, well, when you are done increasing current, the rate of change is going to go to zero, which means change of voltage across the inductor is going to be zero. So all of the battery's voltage now drops across the resistor. So that makes sense that this is the current that will be flowing once that happens. But yeah, the behavior of inductor is very curious. It's unintuitive. It takes a while to get used to. That's why this is the expression you should rely on. And I will say in this maximums case, inductor is not actually doing nothing. It's actually stored energy. Oh, by the way, we did this LR circuit. There's one thing that we didn't handle. I think you know how to do it on your own. Like, what would happen when it's fully charged, as in maximum current is going through the inductor? When you flip the switch over to the other side, what would happen then? Like, this is like the capacitor discharging, right? So when you flip the switch over, let me just tell you what's the interesting thing here. The current through this thing, even though there will be no battery, it doesn't immediately go to zero. Why not? So let me draw the circuit so that you can imagine it better. So, you know, when I flip the switch over to B, then this is what the circuit ends up looking like. So you know, at some moment where the maximum amount of current is flowing through the inductor, this is what I do. Flip the switch over to here. So that means none of this part of the circuit does anything anymore. And this is the circuit you have now. There's no battery in there. There's no capacitor to provide any kind of, you know, potential energy. But this current will not suddenly drop to zero. It'll actually continue to flow for some time. Yes?
Because the magnetic field that's inside the inductor changes, and that creates back induced voltage.
You could understand it that way. And in the circuit context, all of that induced voltage is wrapped up into this expression here, right? So this voltage is the induced voltage. So how does this voltage get induced?
The magnetic field goes.
I don't want you to go back to magnetic field. That's why I was referring to this, because we are talking about the circuit. Any kind of thing dealing with the magnetic field, it's been all wrapped up into L and I. Like, if you're not able to do this, then you didn't really understand it, because you memorized one way of explaining something and you're just repeating it again and again. Yeah. So how do you explain, in the circuit context, why this current does not simply just drop to zero right away?
Because of the rate of change of time.
Yeah. So, I mean, you cannot have an infinite rate of change of current. So current has to change at some rate. And as it's changing, there's going to be voltage change across the inductor, which will be the voltage change across the resistor that's needed to drive the current through it. So I guess the way I prefer to think of it is that this current flows. As it flows through the resistor, there's a voltage drop. That voltage drop is the voltage across the inductor that's now causing the current to change. Anyway, so I think going through the math, it will be a mirror image version of the RC circuit, discharging RC circuit, except it's less intuitive, because what's discharging is actually the energy stored in the inductor. So that's the energy stored in the magnetic field inside the inductor. So, you know, in that sense, it's less intuitive, but the math is actually as simple as the RC circuit. Yeah?
You're saying that the voltage drop across the resistor is the same as the voltage across the inductor because of Kirchhoff?
Let me label some points. Point A and B. Can I say the voltage change across the resistor is voltage change from A to B? Okay. Can I also say voltage change across the inductor? Just the absolute value is a voltage change from A to B. Right? Wire, inductor, wire. That's why. Because of the way they are connected. It's in a loop with only just these two.